Okay, I'm going to give you a quick overview of this periodic table that you've got for organic chemistry, what each part means, when it's going to be relevant to us. Okay, so first of all, you'll notice this periodic table looks a little different from a typical periodic table, and that's because I've taken out the elements that we're not going to use in this course. So basically, I've stripped it down from 100 elements to say, between 10 and 20 elements that we're actually going to use in organic chemistry. And for each one, I tried to give you the most relevant information. Um, so first of all, you've got your element symbol and name. Symbol and name, two important pieces of information in each box. You've also got the atomic number. Where this is relevant for us, remember, atomic number tells us the number of protons in the nucleus. Most of the time, that doesn't really matter for us. The only time it matters is sometimes we in the course of giving these special designations of R or S or E or Z to what we call the stereochemical configurations, then we compare atomic numbers of atoms. But for us, we're very rarely actually going to use this, but it will come up in modules 7 and 8 a little bit. The number of protons is important, but in your first chemistry class, you probably talk more about it than we will here. What we really care about is the number of valence electrons. Number of valence electrons essentially tells me how many dots that atom would have around it when I first draw a dot structure of it. So for example, this tells me that carbon, if I were to draw a dot structure for carbon, I put a C with 4 dots around it. Remember, we're usually trying to get to 8 dots or 4 pairs of electrons around an atom. So that number of valence electrons is going to be important to us. We also use that whenever we're trying to calculate formal charge, because we compare how many electrons an atom has in a particular structure to how many valence electrons it had when it was born. Similar to number of valence electrons, I do give you the valence energy level. Really, where that's important is in the size of the orbitals. We talk about this in modules 5 and 10. But the bottom line with that is the higher the valence energy level, the bigger the orbitals are going to be. And that plays a role for us when we think about the way atoms bond to each other. When I talked about valence electrons, I mentioned formal charge. For each atom, I give you the common formal charges in order from most common to least common. For most elements, the most common formal charge is 0, right? So most of the structures you see will have 0. So you see for most elements, 0 is listed first, except for these metals over here, lithium, sodium, potassium. Those you are usually going to see in their ionized form where they have a +1 charge. And very rarely we see them with a neutral charge, although that can be useful. Probably not in this course, but in future courses, you might see neutral sodium or neutral lithium used in a reaction, and usually used to give away electrons. But the reason I give you these common formal charges, when you are drawing structures and you draw an atom with a particular formal charge, you might want to check, is that one of the common formal charges that I'll see? One trend I'll point out is very rarely do we see a +2 charge. In fact, sulfur is the only one that we're probably going to see as a +2 in the course. most of the time your formal charges will be 0, +1, or -1, depending on the element. And so that can be helpful as you're drawing structures to kind of check yourself and say, well, is this a formal charge that should be expected? And like I said, each of those is listed in order from most to least common. So most often you'll see 0 formal charge. You'll see carbon with a positive more frequently than you'll see carbon with a negative. You'll see nitrogen with a positive more frequently than you'll see nitrogen with a negative. But for oxygen, it's reversed. You'll see oxygen with a negative more frequently than you'll see oxygen with a positive. And then the last thing that's listed for each element is this electronegativity value. We use this a lot. This concept of electronegativity, this is electron pulling strength. And it's really the exact number is not a thing we care about so much, but what we care about is the relative strength when two atoms are bonded together, because a stronger atom is going to pull electrons closer to itself than a weaker atom. So this comes up in Module 1, comes up a lot in Module 2, and then throughout the course. So Module 1 and 2 especially, and throughout the course. And some things I want to point out here, we have a few elements way over on the left-hand side that have very low electronegativity values. These we call the metals. And really, all these other ones that are grayed out are down here. Also metals that might come up in a future orgo course. The key thing to know about metals is they're so weak that they lose electrons. Easily and become positive ions. Okay. So when something's a metal, we're often going to see it just with a positive charge. And in an organic chem class, we usually end up ignoring those positive ions. The rest of the elements on this periodic table are called nonmetals. They're going to bond by sharing electrons. So they'll do covalent bonding. And notice they all have significantly higher electronegativity values than these metals. Aluminum is kind of a special case that you may or may not see aluminum in this course, but you'll see it when you take orgo in college. We treat it sort of like it's a nonmetal, even though it is a metal. So that is my introduction to your periodic table and some of the most important features of it. Please be familiar with it, refer to it often, know what these numbers mean and when they're important to you. I will, in a separate video, talk about the references on the back.